Mr. Heffern here, and this is just a short video to show you where the force field energy equations come from. We're going to derive them. So force field energy, we're going to derive the energy equations for gravitational and electric non-uniform force fields. First, we're going to have to just review some calculus, some derivatives and integrals, which were actually part of Newton's Philosophiae Naturalis Principia Mathematica, published in 1687. So really, physics and calculus go hand in hand. They were invented at the same time by Newton so that he could do physics. So just recall a non-uniform point source force field. We pretend that the force field originates from the central point of an object. Really, though, you can only access it from the surface of the object and outwards. And it's strong at the surface and really weak when you move far away. So either for gravity or electric, doesn't matter. Okay. So now just to go over a derivative again. How does a derivative work? So what is a derivative, first of all? Well, if you have a function like this red line right here, the slope of a tangent line is your derivative. And when you calculate the slope of a tangent line, well, slope is your rate of change, how quickly things are occurring. So for example, let's say this is just part of the this function here. Y equals 5x cubed minus 3/4 x squared plus 0.8x minus 7. You want to find out how quickly things are changing or what the slope is. You want to take the derivative. To take the derivative, there's two things you have to do. Multiply by your exponent and then subtract 1 from your exponent. It's just two steps. So to do that, what we're going to do is just write all the exponents first. We got an x cubed, an x squared. When you have an x, that's really x to the 1. And when you don't see an x, that's x to the 0. So what we're going to do is we're going to take our exponent, so like 3, multiply in front, subtract 1 from the exponent. Take the 2, multiply in front, subtract 1 from the 2. Take the 1, multiply in front, subtract 1. And take the 0, multiply in front, and subtract 1. So anytime you have a constant like 7, okay, with x to the 0, you multiply by 0, you're going to get nothing. So it's going to be gone. And so one way to write the derivative, this is the change in y with respect to x, dy dx. You can just write y prime, means the same thing. So we're going to get 3 times 5, 15, x squared. 2 times 3 over 4 is 6/4, or 3/2. X to the 1, or just x. And then we got 1 times 0.8 times x to the 0, or just 0.8. Subtract 0. And so the slope of the equation is 15x squared minus 3x over 2 plus 0.8. So if we want to go to 2, where 2 is located right here, and find out what the slope is at that point in time, it would be 15 times 2 squared, subtract 3 times 2 over 2 plus 0.8. There would be a slope of 57.8. So that's how you take a derivative. So let's do some derivatives with actual equations of physics. So if you take the change in position equation, delta D is equal to VIT plus AT squared over 2, one of the equations of motion. Remember, delta D is just dF minus DI. So I'm going to take the minus DI and bring it over to the other side. And so this is how you could write the equation of motion right here. So dF, your final position, is DI, your initial, plus your initial velocity, VIT, plus your acceleration, t squared over 2. We're going to take the derivative. If you want to find out what your change in final position is with respect to time, dF dt, the ddt of that, we're going to take the ddt of the other side. So we need to make sure everything here is a function of time. So you don't see a t here, so that's really t to the 0. We got a t to the 1. We got a t squared. And we're just going to do the same derivative thing. So you multiply by your exponent, subtract 1 from your exponent. So multiply by 0, we get 0. Multiply by 1, we get vi t to the 0. And multiply by 2, we get 2 over 2 a t to the 1. And look at that, we just derived one of the equations of motion. Vf equals vi plus at. So there you go. And if you take a look at our equation, acceleration is change in velocity with respect to time. We get that equation right here. Vf equals vi plus at. What happens if we take the derivative of this? So we want to find out the change in final velocity with respect to time. So d dt of Vf. So we're going to take the d dt of vi at. Remember, that's t to the 0 and t to the 1. multiply by 0, multiply by 1, subtract your exponents, and look what we get. Acceleration is acceleration. There you go. So, just to show you, you can do that with derivatives. That all these equations we've been using are really just calculus in disguise. A couple more derivatives which are useful. Newton's second law really is a derivative of momentum with respect to time. So your force, which we usually write as F equals ma, it's all really the derivative of your momentum. So we take the d dt of our mv, and this is going to be chain rule if you know anything about calculus. We have two variables which can change. So we're going to take dm dt over here times the instantaneous velocity, and then we're going to have m times dv dt. Now usually we don't have changes in mass unless we have a rocket like over here. So usually this would just be 0, and dv dt is your acceleration, F equals ma. And there you go. So second law is actually a derivative of momentum. Okay, so now let's take a look at the opposite of a derivative. We call these integrals. Some people call them antiderivatives. And all you do is the exact opposite steps. For derivative, it was multiply by the exponent and then subtract 1 from the exponent. This time we do the complete opposite steps in the opposite direction. Add 1 to the exponent and then divide by the new exponent. So for example, let's say we have, and what is an integral? It finds the area under the function. So if you want to know the area under a weird function like this, you can. For example, if we want to know what this shaded area is from 1 to 5, we can find out. So we have our equation, 15x squared minus 3x over 2 plus 0.8. Remember, so that's really x squared, x to the 1, and x to the 0. And now we're going to do the opposite of a derivative. We're going to add 1 to the 0, add 1 to the 1, add 1 to the 2 there, and then divide by the new exponent. So we're going to get 15x to the 3 over 3, 3x to the 2 over 2 times 2, which is 4, and 0.8x to the 0 plus 1 over 1, and we get 0.8x. And we're going to go from 1 to 5, so that means we're going to use our answer twice. And you're always going to take the top value and subtract the bottom value. So we're going to sub in the 5, so we get 5 times 5 cubed, subtract 3/4 of 5 squared plus 0.8 times 5, subtract, and then we sub in the 1, 5 times 1 cubed, minus 3/4 1 squared plus 0.8 times 1, and we get an answer of 605.2. So whatever that is, that's 605.2 units. So that's an antiderivative or an integral. So where do we actually use integration in force fields and in physics? Well, it turns out that the integration or the integral of a force versus position graph is the work or the change in energy. So we're going to check this out. So here we go. We got a 50 kilogram person, like Spider-Man here, standing near the surface of the Earth. A 50 kilogram person is going to have a weight of 110 pounds or 490 newtons using scientific units. And if Spider-Man climbs a ladder from 0 to 10 meters, what's going to happen? Well, Spider-Man is still going to weigh 490 newtons the entire time. And we just want to see how much the change in energy is, how much work Spider-Man must do for this to happen. So we're going to do the integration of the force of gravity with respect to its position, change in position, from 0 to 10. So force of gravity is mg, so we get mg dr. We integrate it. So this is technically r to the 0. So we add 1, we get r to the 1, divide by 1. And we get mg r over 1, and we get mgr. And we're going to go from 0 to 10 meters. So we sub in the 10 meters, and then the 0 meters. 0 is just going to give us nothing. And so we get mg change in r. And usually we call this change of r h, or your height. And we get 4,900 newtons. So as you see, when you integrate force on with respect to its position, you get work, or we get our gravitational energy equation from a long time ago. So that worked in a simple situation. How about now using universal gravity? So now, for example, what if Spider-Man climbed from the surface of the Earth all the way up to a big space ladder, which is 2 Earth radii high? So we're going to go from 1 Earth radius, the surface of the planet, to 3 Earth radii on a ladder which is 2 Earth radii high. So we know on the surface Spider-Man has a weight of 490 newtons. And if we triple our distance from the Earth, it's going to be 1/9 of the force of gravity. So 1/9 of 490 is 54 newtons. So Spider-Man is going to lose a lot of weight, going from 490 newtons to 54 newtons, while still maintaining 50 kilograms of mass the entire time. So now we're just going to find out how much energy is this, how much work is done on Spider-Man to do this. So we're going to do the same thing. We're going to integrate from the surface to 3 Earth radii, so the Earth radius plus the 2 we climb. So we're going to go from 1 Earth radii to 3 Earth radii, and we're going to sub in the universal gravity, gmm over r squared. And so we get, we integrate that, so that's r to the minus 2. So if you bring r squared from the bottom to the top, it's r to the minus 2. So we're just going to add 1 to that, and then divide by our new exponent, and we get gmm over r. In fact, that's the equation for universal gravity for energy, gmm over r. We're just missing a little minus sign issue. Okay. So we plug in the values. So remember, we have a constant of gmm, so we can sub them to the side. We're going to go from, we're going to finish off at 1 over 3 Earth radii, subtract 1 over 1 Earth radii, or 3/3. 1/3 subtract 3/3 is 2/3. And so we're going to get a work of 2.04 times 10 to the 9 joules. Okay, just a little sign error, don't worry about that. Okay, so there you go. When you integrate the force of gravity, you get gravitational energy. That's simple. So let's see, and the same thing happens for when we do electric forces. So since the formula kqqq over r squared looks like gmm over r squared, we already know what we're going to get. We're going to get very similar situation. We're going to get kqqq over r for our energy equation. And so in this situation here, if we have a Van der Graaf of 70 microtesla, and we want to move an electron from 1 meter to 10 meters, in that case, it's going to be easy. It's going to be reflected away anyway, or deflected, repulsed, I should say. So it's going to have a force of around 1 femtonewton, and we're going to get to like 100 femtonewton from when it was close by. And the work would be 9.072 times 10 to the negative 14 joules. Okay, so force of gravity, the simple formula is mg. The simple formula for electricity is QE. The universal formula is gmm over r squared for gravity. For electricity, it's kqqq over r squared. Oh, there's a little typo there. There's a minus sign. We'll get rid of it. Okay, typo fixed. Right. So, and for universal gravity's energy, it's gmm over r. But it's always negative because this is energy you have to overcome to get away from the planet. You're technically in a gravity well, they call it. And then over here, you got your electrical energy is kqqq over r. So you notice the difference between a force formula and an energy formula. You get an r squared to an r. That's pretty much the only difference. Okay. All right, so here's an example with a gravitational field. Let's say you want to stick a probe from the surface of the Earth to a height of 1,000 kilometers. So this will just get it to the height. It's not going to put it in orbit. You'd need more energy to put it in circular motion. So how much energy would that be? So we're going to use the g, the m of the Earth, mass of our 100 kilogram probe, radius of the Earth plus the altitude we want to put it at. You would need, this is how much energy you would have at that point in time, 5.405 times 10 to the 9 joules. Or that's how much negative gravitational energy, keeping it in the Earth's gravity well. If we use the old formula, mgh, you'd see we get the wrong answer, 9.8 times 10 to the 8. So it ignores the negativeness of the gravitational energy, and it's not even the same magnitude. Not good. Now for an E field, what's the energy on a proton, the electric potential energy on a proton when it's 5 meters away from this negative Van der Graaf? So we got kqqq over r, so 9 times 10 to the 9 times negative 70 times 10 to the 6 coulombs for the Van der Graaf, plus 1 elementary charge, positive charge for the proton, 1.6 times 10 to the negative 19, divided by the 5 meters. It's going to have an attractive energy of 2.016 times 10 to the negative 14 joules. It's not too far off from the simple formula for parallel plates. This formula only works for parallel plates, doesn't work for non-uniform force fields, but if you accidentally did it, you would get a very similar ballpark answer. Okay, so in summary, force field energy is derived by integrating force over change in location. The equations are pretty simple, as you can see. Okay, the big difference between force and energy is an r squared versus an r squared versus an r, and I hope this helps. Thank you.